Hello and welcome. Why do seagulls fly over the sea? Because if they flew over the bay, they'd be bagels. If you're wondering why that joke was a little bit below average, it's because today we're going to learn about the average value of a function over an interval. We better get started before the jokes get any worse. So the question again is, how do we find the average value of a function? More specifically, a continuous function. And down below we've got a little picture of a surfer surfing on a sine wave. Yep. Little alpha fish, right? Some plus seaweed. Okay, getting distracted. So as an example, in figure 1 we have some function, and we want to find the average value over the interval from a to b. Now notice when you compute the average value of a finite number of numbers, what you do is you add them all up and then you divide by the number of numbers. So like let's say you wanted to find the average of 7, 4, and 8. Well, you would take 7 plus 4 plus 8, figure out what that is, that's 19, and then divide it by 3. So the average value would be 19 over 3 in that case. But what if we want to find the average value where we have an infinite number of values that we're putting together, right? So that on this interval from a to b, there are an infinite number of y values because there are an infinite number of x values from a to b. So how can we compute the average value of such a function over an interval? Well, just like we have done before, we can take our interval, chop it up into a bunch of subintervals. So here a to b is chopped up into x sub 1, x sub 2, x sub 3, all the way up to x sub n. So this is n x values that we're looking at here. And once we have done that, we have a finite number of x values. So we can find the average value by adding all those x values up and dividing by the number of x values. Now we're going to do this step in just a moment, but to help us out before we get there, note that the way we computed delta x, which is the width between each of these x values, the subinterval width, is we take the full width, which is b minus a, so it's the full interval width, and divide it by the number of subintervals, so divide it by n. More useful to our particular case is going to be to solve for n. So we can take the same equation, multiply the n over to the left, and divide the delta x over to the right. So this is just another way of writing this exact same equation that we just wrote right here. And we're going to hold on to this for just a moment. We'll whip it out when the time calls for it. So to find the average value of f over that interval, we'll do this. We'll chop up our interval into a number of subintervals, into n subintervals, and we'll have, actually n minus 1 subintervals, I guess, and we'll have the sum then of all the function values divided by n. That's how we can get the average value, or an approximation for the average value on that subinterval. The more subintervals we use and the smaller the subintervals get, the more of these function values we're going to be adding together, and the n will get bigger on the bottom and the sum of the function values will get bigger. But in the limit, this is going to approach the average value of the function, because the more y values we use in our computation, the better the average value is going to be. The more close it's going to get to the infinite, into accounting the infinite number of y values. And the first step we're going to take is replacing the n with b minus a over delta x. So that was the step that we just looked at a moment ago. Now we can, to divide this fraction, we can flip and multiply. So dividing by the fraction is like multiplying by the reciprocal, so the delta x would multiply up to the top. And this b minus a on the bottom here, that can be pulled out of the limit altogether. This is pulled out as a 1 over b minus a. Now what we have left is the limit as n approaches infinity of the sum of these x values. This is actually like a Riemann sum going on right here. In fact, if you distributed the delta x to each of these terms, you'd have exactly some kind of Riemann sum. This is just another form of the Riemann sum. So this limit here turns into, by definition, a definite integral. This is the definite integral from a to b of f of x. Now the 1 over b minus a as a constant is just hanging around on the outside. So now we've arrived at a formula for finding the average value of a function over an interval. It's 1 over b minus a, so 1 over the interval length, times the integral from a to b of f of x. So it ends up being a very simple formula involving integration. So this is just giving you the definition, kind of a formal way of doing it. Now it's boxed, so it must be true. So let's take a look at the notes for the first example. In example 1, we're asked to find the average value of f of x equals sine cubed x cosine x on the interval from 0 to pi over 2. And now that we have a formula to find the average value, which is our favorite formula, f sub average, or av, we can just kind of plug and chug. So we have 1 over b minus a. b here is the pi over 2, and a is 0, start and the end of your interval. And then the integral from 0 to pi over 2 of the function sine cubed x cosine x dx. What kind of technique are we going to use to evaluate this integral? If you said substitution, then that would be correct. And what would you let u equal to? So sine x would be a great choice for u because the du is cosine x, which is appearing right there next to the dx already. Now we do have limits of integration that are in terms of x, and when we're making a substitution like this, I recommend that you change your limits of integration when you change your variable, so that everything in the new integral will be in terms of u, and you never have to look back to the old variable x. So when x is equal to 0, that lower limit of integration, u is equal to sine 0, which is 0. And then when x is equal to pi over 2, you have u equals sine pi over 2, which would be 1. So our integral looks like this. Well, first off, the 1 over pi over 2 would become 2 over pi. And then x equals 0 becomes u equals 0. X equals pi over 2 becomes u equals 1. Then you have sine cubed becomes u cubed. And then you have cosine x dx, which is du. So now at this point, we integrate. We find our antiderivative. Plug in the 1, plug in the 0, and you'll get 2 over pi times, I'll just write 1/4 minus 0, which is 1 over 2 pi. So whatever that number is, that represents the average value of this function over the interval from 0 to pi over 2. And that's it. Thanks so much for watching. See you next time.